we've seen that sometimes we can express differential equations involving functions of more than one variable. And sometimes when this happens, we will need to know how you take the derivative of a function of more than one variable, especially when there's other things going on. So we quickly need to talk about the multivariable chain rule. So you've no doubt seen the chain rule in the context of, say, you have z is some function of y, and y is some other function of x. Then you use the chain rule to figure out what is dz dx, right? And the single variable chain rule says that dz dx is dz dy times dy dx. Okay, but this is how it works out when everything is just a function of a single variable. We're going to look at a situation where z is a function of both x and y. So the situation we have here is z is a function of x and of y, and then in turn x and y are both functions of some other variable, say t. Okay, now I'm just going to write down what the chain rule is without really justifying it. And it looks like this. The derivative of z with respect to t, right? We can regard z indirectly as a function only of t, and so it should have a regular derivative. It is the derivative of the function f, which really is z, right? The derivative of f with respect to x. And remember, what this means is you take whatever formula shows up here, whatever mixture of x's and y's shows up here, you take a derivative treating x like the variable and treating y like the constant. So x gets treated like the variable for this derivative, and y gets treated like a constant. And then you multiply by the derivative of x with respect to t, plus, and then you do the same sort of thing, but for the y's. You get derivative of f with respect to y, and again, for this derivative, x gets treated like the constant, and y gets treated like the variable, and then you multiply by dy dt. Okay, so the way to remember this is each individual piece of this multivariable chain rule looks very similar to the single variable chain rule, right? You have the derivative of your top level thing with respect to the middle level, right? Derivative of the top level with respect to the middle level times the derivative of the middle level with respect to the bottom level. That's x and t. The only difference with the multivariable chain rule is since there's more than one middle level, you get more than one term, right? But again, it's top level with respect to middle times middle with respect to bottom, and then each of these terms get added up, right? So with that in mind, let's try out this multivariable chain rule. So again, I'm not trying to justify why this is the correct chain rule. You're going to have to take my word for it. So let's try it out. So let's so z is x squared times y, and let's find dz dt. So it's sort of implicit in this is x is really some function of t, and y is also some function of t. So when we ultimately get derivatives of x and y with respect to t, we'll just leave them because we don't know what these functions are. Okay, so our formula says that dz dt is the derivative of z, or f, same thing, with respect to x times the derivative of x with respect to t, plus the derivative of z with respect to y times the derivative of y with respect to t. Okay, now some of these derivatives we can evaluate. So this one, for example, partial derivative, missed my color change, partial derivative of z with respect to x. So we look at our formula for z here, and we take its derivative, but we treat x like the variable and y like a constant. And since we're treating y like a constant, we don't have to do any product rule here, right? We can just use the constant multiple rule. So take the derivative of the x squared part, you get 2x, and then the constant just sort of survives the derivative like that. times dx dt. Since we don't have a formula for what x is as a function of t, we just have to leave this as dx dt. Okay, plus, now derivative of z with respect to y. So now we take the derivative of this formula for z, but we treat y like the variable and x like a constant. So the x squared just survives since it's a constant multiple, and then derivative of y is 1. So we're done with this derivative of z with respect to y. So then times dy dt. And again, since we don't know what y is as a function of t, we have to just leave it like that. So there we go. There's our formula for the derivative of z with respect to t. All right, let's look at one more example. If z is y times cosine x, let's find dz dx. Now this is different than our previous examples because, right, we have z depends on x and y, and then x. So since we're taking the derivative with respect to x, I'm sort of implying that x is the bottom level variable here. So x depends on x in a way that we understand because x is equal to x. But y also depends on x somehow. So that's sort of implicit in this setup that y is somehow a derivative of x. Or I'm sorry, y is somehow a function of x. Okay, so let's find dz dx. So according to our multivariable chain rule, this should be derivative of z with respect to x times the derivative of x with respect to our bottom level variable here, right? It's top with respect to middle, and then middle with respect to bottom. So that's another x right here, plus then dz partial z partial y. So top with respect to middle, and then d middle with respect to bottom, like that. And again, some of these derivatives we can work out. So dz dx is, now a derivative of z with respect to x, right? We take this formula for z, and we take its derivative, treating x like the variable. So we get minus y cosine, sine x times dx dx. Now this we can evaluate. That's just 1, right? Derivative of x with respect to x is 1. Plus derivative of z with respect to y. So now we take the derivative of our formula for z treating y like the variable, and we got cosine x times dy dx. And since we don't have a formula for how y depends on x, we have to leave that alone and just leave it dy dx. So the whole thing is minus y sine x plus cosine x dy dx. And there we go.